All right. Today we're going to be looking at what are called the colligative properties of solutions. It's just a fancy word, colligative. And what it means is that adding solute changes the properties of a solvent. The properties that we're going to be discussing today are things like vapor pressure, which is how quickly a solution evaporates at a particular temperature. Boiling point is another good example. The amount of heat you have to add to get something to boil. And something called freezing point. And we're going to indicate these two temperatures, TB and TF, for boiling point and freezing point. And what happens is that adding solute changes these properties. It makes things more difficult. It makes it harder to get something to boil. It makes it harder to get something to freeze. Let me show you what we're talking about here. Here is a pretty good example of what's going on with water. We've got all of our little water molecule buddies. They all look like little Mickey Mouse, and we're currently at negative 233 degrees Celsius, well below water's normal boiling point of 0 degrees Celsius. And notice that they're all kind of locked together. They're all locked together in this orientation that means there's lots of space in between molecules. See what I'm talking about? And then as we heat it, and this temperature increases pretty quickly, we'll try to stop it right around change. Notice that we're still below 0 degrees Celsius. We're at negative 24, and they're still locked together, but man, are they bouncing around. But they're staying pretty well stuck together. As we get close to 0 degrees Celsius, notice they're not really locked together anymore. They're kind of bouncing around and twitching. And as we change our temperature, notice that they get a little closer together, but that their orientation isn't really fixed. So they're sticking together. We know this. Water molecules are polar, so they stick together, and they're not forced into that locked together orientation that solid water, what we call ice, is. And of course, as we heat this, the hotter they get, the faster they move. And as we approach water's normal boiling point of 100 degrees Celsius, they start breaking loose from each other a little bit better. Now, what's going on is what we call boiling. And if we continue to heat this, they continue to move faster and faster until the distance between them grows and they are no longer in what we call the liquid phase. Pretty interesting. But as we start adding solute, this changes. This one's a little bit simplified. Here's our pure solvent. This is just going to be regular water. Now, we don't have our Mickey Mouse molecules anymore, but they are all the same color, so we're going to assume that they're all water. Over here is a solution. This is water molecules with some solute particles, and we're going to stick with this look right here where our solute particles are just one type of atom. What we're going to do is we're going to run this simulation, and we're going to watch how quickly it takes the water to evaporate. Remember that water vapor is caused by the tendency of these water molecules to leave this surface and just off they go. We're never going to get them back again. And of course, as that happens, the amount of water in the vessel drops and evaporates. Let's watch what happens, because for water molecules to evaporate, they have to leave. What happens is that when there is solute particles in the way, it makes that more difficult. So let's watch what happens. We'll hit run. And you can observe the level at which this water drops. You can also count the number of water molecules that actually make it out of the solution, and it looks as though our pure solution, our pure solvent, just regular water right here on this side, it's a little bit faster. Wow, that's starting to take off pretty quick. And notice that over here, some of these water molecules are having a hard time leaving because due to their polarity, remember, they're polar molecules, they have a tendency to stick to stuff. It makes it harder to leave. And so these water molecules constantly get stuff in the way. What does this do to properties like freezing point or boiling point? Let's take a look. Because, let's make that a little bit bigger. Because adding solute makes it more difficult to boil, it means that we must add more heat. Than for pure solvent. What this is going to do is make it harder to boil. And so it's going to alter the boiling point. The temperature at which the water boils becomes higher than otherwise. And what this means is that you have to add more energy, and the water, which would normally boil at 100 degrees Celsius, won't boil at that temperature. You have to heat it even harder. It works the same way for freezing. Adding solute makes it more difficult to freeze, because water has to form those really close associations, and when there's stuff in the way, it just makes it harder. This means we must cool the water to a lower temperature. And for what our purposes, in this case, what that means is that the normal freezing point, what we're going to call TF, becomes lower than otherwise. Okay, so what determines how much we raise or lower the freezing point? What determines our new freezing point or boiling point is concentration. Obviously, the more stuff in solution, the harder it's going to be. For our purposes, we're going to measure concentration in molality. Let's see how this works. Let's do boiling point first. So this delta means change. So the equation that we're going to use is going to look like this. Change in boiling point is going to be equal to the molality, of course that's the concentration, times something called the boiling point constant. We're going to call that KB, boiling point constant. It is different for every solvent, and there's no need to memorize anything. In fact, I'll show you where we get this from. So now there's no need to memorize anything because I'll provide all this information to you, but here's a pretty interesting table. It says molar freezing point and boiling point constants. So look what it says. Here is a KB for every solvent we might consider. And so look at water. It says has a normal boiling point of 100 degrees Celsius. But the temperature at which it boils in degrees Celsius goes up for every 1 molal of concentration by a little over half a degree of Celsius. So anytime we see that, we'll input this for whatever solvent we have, all right? So let's try one of these. Let's use this molal boiling point constant for water. And let's try one of these. So here's the kind of thing you could expect me to ask. It's going to look like this. Let me get an example here. So this says what would be the new boiling point of a 3 molal solution of water. Let's be careful because all this equation does is tell us the change. So we'd have to find the change and then add that to the new boiling point. So we've got a 3 molal solution. The Kb for water from this table right here is 0.51 degrees Celsius per molal. So what happens to our boiling point? It increases by, let's bust out our calculator. It's a pretty easy calculation. 3 times 0.51 is 1.53, and since molal cancels, we get degrees Celsius. This is our change. This is delta TB. This is not the new boiling point. We'd have to add that. So if our original TB is 100 degrees Celsius for water, and our delta TB is 1.53 degrees Celsius. Excuse me, I hit the wrong button. Oh no, Microsoft OneNote crashed on me. Interesting. Let me pause. There we go. So 1.53 degrees Celsius is our delta. What's our new delta TB? 101.53 degrees Celsius. It works exactly the same way if we're talking about freezing point. So delta TF, freezing point, is equal to molality times something called the freezing point constant. Obviously, this is going to be change in freezing point. This will be molality, and this is our freezing point constant, which, just like boiling point constant, you can find from this table. And it tells you what the freezing point constant is for every different solvent. Here's water, has a normal freezing point of 0 degrees Celsius, and it has a freezing point constant of negative 1.86 degrees Celsius. So that's a real simple calculation. Let's try it. And so let me get a question. So here's a type of question you could expect to see. Now, what this question is asking for is only asking for the change. So there's no need to get too crazy. And so if we know delta TF is equal to molality times KF, we have a molality of 5 molal. And since we're talking about water, what's our freezing point constant? Right there, negative 1.86 degrees Celsius per molal. So we'll plug it right in here, times negative 1.86 degrees Celsius per molal. Notice it's negative because it is lowering the freezing point. It is making the freezing point lower than it would normally be. So let's make sure that our delta is a negative number because it's decreasing. So taking our calculator, I'm going to say 5 times negative 1.86. Notice that molality cancels, and our new freezing point is lower by 9.3 degrees. Now this is only asking for the change, but if it was asking for the new freezing point, if we knew that the original freezing point for water, original TF, was 0 degrees, and we know that our change in delta, our change in TF is negative 9.3, we would simply add our negative, and so our new TF is negative 9.3 degrees Celsius. All right, that's all we're doing, so take it for a spin.